Let's take a counter design problem. Here we are asked to design a counter using T flip-flops, and it's going to count in the following pattern: 101, 001, 110, 011, 111, and then back to 101 and repeats the process. Anytime you hit the reset button, you're going to start with the 101 state. So how do you design this? Again, whenever you're given a counter problem, the first step that you need to do is identify the number of flip-flops required. It doesn't matter if it is T flip-flops, D flip-flops, JK flip-flops, or SR flip-flops. The number of flip-flops are going to remain the same. To get to know the number of flip-flops, look at the pattern. Here, the pattern has 3 bits. Therefore, you would need 3 flip-flops. Next is to construct the excitation table. So to construct the excitation table, first we are going to look at the present state, QC, QB, QA, because we have 3 flip-flops. Next we have QC plus, QB plus, and QA plus. And then finally we have TC, TB, and TA. TC, TB, TA are the inputs to the T flip-flop. QC, QB, and QA are the current states. QC plus, QB plus, and QA plus are the next states. So start with 0, 0, 0. So we have 8 combinations for QC, QB, QA. So if QC, QB, and QA are 0, 0, 0, the next state is don't care, because that sequence never occurs in our pattern. When it is 0, 0, 1, the next state is 1, 1, 0, as shown here. When it is 0, 1, 0, the next state is don't care. When it is 0, 1, 1, the next state is 1, 1, 1. When it is 1, 0, 0, the next state is don't care. When it is 101, the next state is 0, 0, 1. When it is 1, 1, 0, the next state is 0, 1, 1. And finally, when it is 1, 1, 1, the next state is 101. Now we need to find out TC, TB, and TA. So basically, if QC is 0 in the current state and QC plus is don't care in the next state, your TC, TB, and TA will be don't care. So wherever you have don't care as your next state, you can put don't care. Now, when QC is 0 in the current state and QC plus is 1 in the next state, what should be the value of TC? So we need to do the same approach for all the other combinations as well. So to do that, we first need to write the truth table for a T flip-flop. So in a T flip-flop, you have input T, the current state, and the next state. So you have 4 combinations. When T is 0, your Q plus will be Q, so it's just going to hold. When T is 1, that is toggle is 1, if Q is 0, Q plus is 1, and if Q is 1, Q plus is 0. So that's toggle. Now I can write this in a slightly different way. So if Q, Q plus, and T, so you have 4 combinations. You can directly take from this table, or you can like try to construct it. So if Q is 0 and Q plus is 0, then your T can be a 0. Basically, you're holding the previous value. You can only hold the value if T is 0. If Q is 1 and Q plus, if Q is 0 and Q plus is 1, then it's a toggle operation. Therefore, T must be 1. Again, T must be 1. And here, T must be 0 because it's holding the state. Now, using this table, I'm going to input in this table here. So if QC is 0 and QC plus is 1, which is this one here, toggle should be 1. So TC is 1. Again, QB is 0 and QB plus is 1. Therefore, it's a toggle operation. And if QA is 1 and QA plus is 0, then it's another toggle operation. Let's look at this one here. QC is 0, QC plus is 1, so that's toggle. And QB is 1, QB plus is 1, so that's no toggle. Same for this. Let's keep going. This is a toggle operation, non-toggle and non-toggle. Similarly, this is a toggle operation. Next is a non-toggle, and the next one is a toggle. Non-toggle, toggle, and non-toggle. So this is how you can construct the excitation table. Now from the excitation table, you can find the equations for TC, TB, and TA. So for TC, construct the K-map. Your K-map will be in terms of QA or QC, QB, and QA. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So TC would be, TC is asserted when QC is 0, QB is 0, and QA is 1. So 0, 0, 1. It's also asserted for 0, 1, 1. And it is also asserted for 1, 0, 1 and 1, 1, 0. So 1, 0, 1 and 1, 1, 0. And it is don't care for 0, 1, 0 and 1, 0, 0. So 0, 1, 0 and 1, 0, 0. From this, you can find the equation for TC. So let's start grouping up. This is the first group. This is the second group. And this is the third group. E equals QC prime and QA. That is this one here. This one would be prime QA. This one would be QB QA prime. Similarly, you can construct the equations for TB and TA. So let's start with TB. So TB is asserted when it is 0, 0, 1 and 1, 1, 1. So 0, 0, 1 and 1, 1, 1. And it is don't care for 0, 0, 0, 0, 1, 0 and 1, 0, 0. So your TB equation would be this grouping, which is QC prime, QB prime, or this one, which would be QA, QB, QC, or QC, QB, QA. We can also construct the K-map for TC. QC, QB, QA, 0, 0, 0, 1, 1, 1, 1, 0. So TC is asserted, or TA actually. This should be TA. So TA is asserted when you have 0, 0, 1 and 1, 1, 0. So 0, 0, 1 and 1, 1, 0. And it is don't care for 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and 1, 0, 0. So your TA equation would be this grouping here, which is QA prime, or this grouping here, this one here, which would be QC prime and QB prime. So those are the equations for TC, TB, and TA. And then you can construct the circuit diagram using the three equations. So your overall circuit should look as follows. This is T flip-flop C, T flip-flop B, T flip-flop A. Each of them has a clock. So your clock signal goes here, here, and here. Each of them have clear N and pre-N. So clear N, pre-N. Both are active low. Clear N, pre-N, clear N, pre-N. Active low signals or active low inputs. You have a reset. Remember, it's an active low reset. So your initial state is 101. So basically, your flip-flop C should be initialized with 1 or reset to 1. Flip-flop B is reset to 0 and flip-flop A is reset to 1. So it's a 101 reset. So when it's a 101, pre-N should be 0. Here clear N should be 0. And here pre-N should be a 0. This can be connected to logic 1. This can be connected to logic 1. And this can be connected to logic 1. So this is going to reset to 1. This is reset to 0. And this is reset to 1. Now each of them has a T input, TC, TB, and TA. And this is QA, QB, QC. And then you can construct the combinational logic for TC, TB, and TA. So this is combinational logic. So this is the design using T flip-flops.